Welcome to The Explainer. So today, we're actually time traveling back to a foundational moment in computer science. We're digging into a seriously fascinating master's thesis from way back in 1993, written by Cheng-Fan Xu at the Tatung Institute of Technology. And the topic? Robot bin picking. Now, I know that might sound incredibly niche, but stick with me, because the algorithms explored in this very document literally laid the groundwork for the automated world we live in today. Let's get right into it.
Okay, let's dive into this. Think about how easy it is for you or me to just reach into a cluttered bin of assorted Legos or maybe a box of hardware and pull out exactly the piece we want. You don't even have to think about it, right? But for a robot, that simple everyday action requires climbing an absolute mountain of math and visual processing. How does a machine translate a chaotic array of pixels into a physical, highly precise scripting action? That right there was the billion-dollar question of 1990s robotics. To ground these abstract algorithms in physical reality, let's map out a classic pick-and-place setup. You've got the CCD camera mounted up above, looking down at the workspace, basically acting as the robot's eyes. That video signal feeds directly into the vision system, which crunches the image data and shoots commands over a good old-fashioned RS-232 cable to the robot's controller. And finally, that controller moves the heavy mechanical arm. It's this beautiful, continuous loop of hardware and software working together, but for it to actually work, that software has to be perfectly dialed in.
Section 1. The bin picking problem, bridging the gap. So the whole point of this setup is bridging that massive gap between digital perception and physical reality. The camera only gives you a flat image, but the robot arm operates in a physical 3D space. So the absolute crucial starting point is finding what the thesis calls the hold site. Basically, this is the exact mathematically pinpointed location and orientation where the robot's end effector, its mechanical hand or parallel jaws, can actually grab the part without smashing into other objects or just missing it completely. Finding those exact coordinates, that's the ultimate finish line for every algorithm we're about to look at. All right, Section 2. The traditional matched filter, the baseline.
To really understand the baseline solution the engineers were relying on in the early 90s, we have to look at the traditional matched filter. The algorithm here essentially scans the image, hunting for a very specific visual footprint, a dark region, a bright region, and then another dark region. The two dark areas represent empty space where the jaws of the gripper can safely close, and that bright region right in the middle, that's the physical part waiting to be picked up. Honestly, it's basically a highly complex digital version of trying to put a square peg in a square hole. If we kind of look through the robot's eyes here, we can see exactly how the matched filter processes all that visual data. It applies filters to measure the vertical and horizontal responses across the entire image, essentially just seeking out the highest magnitude of contrast. Wherever it gets the absolute strongest dark, bright, dark signal, boom, it flags a potential hold site. It's an elegant but definitely brute force way to scan an image.
Which brings us to Section 3, the fuzzy logic approach, adapting to realities. But here's the catch, right? The real world isn't some pristine, perfectly lit laboratory. Shadows fall, metal surfaces glint in the light, and contrast gets super muddy. When the thesis pits these two methods head-to-head, it reveals a really stark contrast. The traditional matched filter is computationally faster, like it gets to an answer very quickly. But the fuzzy logic method, it delivers significantly higher accuracy. And why is that? Because it doesn't force the image into this rigid binary of, okay, this pixel is definitely dark or this pixel is definitely bright. The author of the thesis actually puts it really well. He notes, it is difficult to say that the pixels having intensities near the threshold value are dark or bright, but it is more reasonable to consider the pixels to be fuzzy. If uneven factory lighting makes a background pixel look even just slightly bright, traditional logic might completely fail to spot the hold site. Fuzzy logic, though, allows the robot to see the world in shades of gray. It assigns a degree of brightness rather than a strict true or false label. It's a total game changer. Now, we're going to skip the heavy math equations here, but we can easily break down how this fuzzy logic operates into 3 pretty intuitive steps. First up, the algorithm averages the pixel intensities within specific windowed regions. Second, it applies what are known as membership functions, and these determine the actual degree to which a region is dark or bright. And finally, it executes a set of fuzzy rules. Think of it like a really advanced flowchart that figures out not just the location, but the precise orientation of the part. And that brings us to these really fascinating histogram models. These graphs show exactly how the fuzzy logic system handles all that varying illumination.
Whether the contrast is incredibly low, or the background is totally flooded with light, or maybe harsh shadows make a region too dark, these models allow the robot to dynamically adjust on the fly. Instead of just failing when the lighting changes, the algorithm shifts its own internal definitions of light and dark based on these histogram peaks. That guarantees a reliable grip no matter what the conditions are on the factory floor.
Section 4, the triangular improvement, the ultimate upgrade.
Building up to the climax of the thesis, the author introduces this proprietary upgrade, the triangular method. So what makes this so special? Well, it acts as a direct extension of the previous two methods, basically taking the best of both worlds to optimize overall speed and accuracy. But the really crucial part? The thesis notes that this improved algorithm is the vital stepping stone the robot needs to take its vision system out of flat, 2D images and expand it out into the real, three-dimensional world.
And finally, Section 5, stepping into 3D space, beyond flat images.
Because you gotta remember, the ultimate goal of this research was never just to look at flat pictures. It was to conquer the actual physical depth of a bin. To pull this off, the author uses the principles of a pinhole camera. It perfectly demonstrates how a three-dimensional object in physical space projects through a camera lens onto a flat, two-dimensional sensor array. By perfectly mastering the 2D fuzzy logic and those triangular algorithms we just talked about, the author proves that you can actually reverse engineer this projection. The robot can calculate the camera's focus, determine the maximum permissible error, and calculate a true 3D hold sight and orientation. Mastering that flat 2D plane was literally the key to unlocking spatial awareness.
So, I want to leave you with this thought. We've just walked through a 1993 master's thesis about a robot looking at a flat image of a parallel jaw gripper. But look at the massive leap in logic here. By realizing that rigid, binary, true or false programming fails in the messy real world, and by teaching algorithms to evaluate shades of gray and degrees of probability instead, researchers like Shangfen Xu were laying the absolute bedrock for modern computer vision and artificial intelligence. The next time you see a high-tech robot seamlessly navigate the world, ask yourself, how much of its genius is simply built on the legacy of learning to pick a single part out of a dark bin? Thanks for joining me on this explainer, and keep learning.